In this video, we're going to talk about the normal distributions, and this is just a basic introduction and overview. In subsequent videos and sections, we will get much deeper into what it means. We're going to start our discussion by talking about random variables. We talked about variables at the very beginning of this course. And now we've talked about probability, and we're just going to put the two together and talk about what a random variable is. We talked about randomness also earlier in the course. We're just going to put all these concepts together and say that a random variable is a variable whose value is a numerical outcome of a random phenomenon. So you know what random phenomenon is. Flipping a coin, rolling dice, those are random phenomenon. Many other things will fall in that. Here's the highlighted thing though. It's a numerical outcome. So we are talking about quantitative data. And we often denote random variables with capital alphabetic symbols. Capital X and capital Y are your most common. So the probability distribution of a random variable X, it just tells us what values X can take and how to assign probabilities to those values. Just like when we made probability models, and we had a sample space, and we assigned probabilities to every event in the sample space, and we made sure that all those probabilities added up to 1, so we have a coherent probability model. Probability distribution for a random variable does the same thing. And random variables can be discrete. This word, discrete. They're discrete, they have a finite and countable list of possible outcomes, and you assign a probability to each of those outcomes. Such as rolling the dice, where we had that chart where we had every outcome possible when you roll 2 dice. That's a discrete random variable. On the other hand, you might have random variables that can take on any value in an interval. And so probabilities now aren't assigned to a single outcome, but now they're assigned to intervals of outcomes. And they're assigned by talking about the area under a density curve. So we're going to have to define those terms. Those are called continuous. So examples of discrete random variables: the number of pets you own, what day of the month it is, how many days of class you've missed. Examples of continuous random variables might be weight or temperature or the time it takes you to travel to work. Remember, the difference is discrete has a finite and countable number of outcomes. Might be a heck of a lot, and you might not have the ability to really write them all down on a piece of paper, but they'd still be finite, they'd end, and countable. So continuous probabilities, again, are intervals of outcomes. Women who weigh between 130 and 135 pounds. There's an interval. What's the probability that a woman weighs that? That's an example. You cannot assign a probability to each individual outcome because there are an infinite number of outcomes. Somebody could weigh 130.1267593. One could weigh 130.1576994, and you can have the halfway in between there. There's just an infinite number of outcomes, so you can't peg each one because you can't count them up. And again, we're going to use the area under a density curve. So again, this is something we're going to have to talk about, define, and understand. So a density curve is some kind of curve, picture, graph, that has an area of exactly 1 underneath it. And that corresponds to a total probability of 1. Remember, a probability model has to have all the probabilities summed to 1. Well, if we're going to use intervals on a density curve, we got to make sure still that all of our probabilities for everything that could happen can't go over 1. And so it's the area under that curve that is 1 that corresponds to that total probability of 1. Now the probability model, the continuous probability model that we focus on in this course is the normal probability model. There are a lot of other ones, but this is what we focus on. So we're going to discuss this in depth. I just want you to be aware that there are others, and that if you went further in statistics, you would encounter other continuous density curves that would be very useful. This is the one that's often used to assign probabilities to intervals. And part of the reason for that is because so many things end up, the data looks like a normal curve, which is very common. And you'll see that as we go on. They are probability models. You assign probabilities to intervals of outcomes. Let me bring that back up. Okay. So normal curve. We need to look at what that looks like and what its properties are. So the shape of a normal distribution, you're going to hear this over and over again. So many population distributions fall into this shape, into this normal curve. They are bell-shaped and symmetrical. That means that they are not skew right or skew left. They're symmetrical. That is a term that we learned very early on in this course. If you don't remember what that means, I want you to go back in your notes and review that. It's bell-shaped, so it's unimodal. If you don't remember what that word means, I want you to go back and review that. And the bell shape can be different for different normal distributions. They're not always the same. Here's 3 different ones to look at. This green one has a mean at -2. It means half of it is greater and half of it is less. And the standard deviation, which we denote by sigma. This is a Greek letter sigma, and this is the Greek letter mu. Okay, those are the symbols we use for mean and standard deviation of a population. The standard deviation here is 1. Here we have a much taller, skinnier version of the normal curve because it's got a smaller standard deviation. That brings all the data together, and it's centered at 3. And here we have a much squatter and wider normal curve because it's got a bigger standard deviation, which gives it more variation, right? It brings the data out further. So all concepts we learned when we were talking about means and standard deviations. And the shape of a bell curve is completely determined by the mean and the standard deviation. That's all you need to know to determine what your bell curve looks like, what your normal curve looks like. Some examples. Data that tend to be normally distributed. Heights of men. The duration of pregnancy. Let me bring it back to that. Sorry, I thought that was another one. So you can see that both of those will be centered at their mean. They don't give standard deviations here, but they're centered at their mean, and then they follow that normal bell-shaped pattern on both sides from there. Okay, I'm going to keep reviewing this. You're going to hear me say this over and over. A normal curve is symmetric and it's bell-shaped. Make sure you understand what those words mean. Its shape is completely determined by its mean and standard deviation. Those are the critical pieces of information when talking about a normal curve or a normal distribution. The total area under a normal curve, just like any density curve, is equal to 1. We'll also use percents interchangeable with the proportions or the decimals like we did with probabilities, and so that would be the analogous to 100%. And the x-axis is a horizontal asymptote for a normal curve. That means on both sides, the normal curve comes down really, 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 really close to the x-axis, but it never, ever touches it. And we denote the random variable by saying x, our random variable, follows a normal distribution with the mean of mu and a standard deviation of sigma. That's the notation we'll use. So if we have something that follows a normal curve or a normal distribution, we'll write an n, and then in parentheses we'll write whatever the mean is and whatever the standard deviation is. This is our typical notation that we use. It's very important that you recognize that notation. Okay, you remember this, I hope, from when we talked about standard deviation. We're talking about variation, and we talked about how there is this one special distribution, one special curve, one special shape of thing, where you have approximately 68% of the data falling within one standard deviation of the mean, approximately 95% of the data falling within two standard deviations of the mean, and approximately 99.7% of the data falling within 3 standard deviations of the mean. Well, what we were talking about there was the normal distribution, the normal curve. Introducing that concept early on, we will be applying it more now. Standard normal curve, continuing with the properties of the normal curve. Now we're talking about the standard normal curve. So like I said, we can have a mean and the standard deviation of anything for our normal curve. But what's going to be helpful for us is to be talking about the normal curve with a mean of 0 and a standard deviation of 1. Called the standard normal curve. And these z's up here and the arrows, that'll all be explained as we go further on. But basically, the concept that I want you to get now is that we can take any normal curve and we can see where we are analogously on the standard normal curve. We can do what we call standardizing it. And that helps us to find the probabilities in different intervals. Okay, so let me tell you what the properties of the standard normal curve are. It is symmetric and bell-shaped, just like any normal curve. It has a mean of 0 and a standard deviation of 1. That is the key specific information that distinguishes the standard normal curve from any other normal curve. And so we write n, and in parentheses 0, 1 to denote a standard normal curve or a standard normal distribution. And just like any other normal curve, the total area under the curve equals 1. Pretend that's a 3 there, because it should be, and I don't know why it's not. So those are the properties. Notice the only distinct property of the standard normal curve is the mean of 0 and the standard deviation of 1. That is the key information about the standard normal curve. In the next video, we'll talk about how to take any normal curve and standardize it so that we can find some of those probabilities of intervals in the distribution.